Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
Good day, grade 8 learners. Welcome to today's Natural Sciences lesson. My name is Papa Singo, and this lesson is proudly brought to you by the Harding Department of Education. In today's lesson, we're going to be learning under the knowledge area, energy and change. The topic is visible light, and the subtopic, which is our main area of focus today, is radiation of light and spectrum of visible light. So now let's look at today's lesson objectives, which are the goals that we aim to achieve by the end of today. So at the end of the lesson, you should be able to explain that light is emitted from luminous objects, explain that light travels in straight lines, explain what happens when light is dispersed by a prism, and explain how a rainbow is formed. And all of this is found on your CAPS document on page 50. Now, let's look at pre-knowledge. So this has basically led us to today's lesson. In the 7th grade, we learned about the transfer of energy, especially solar energy. We learned about solar energy in the 7th grade. Now, let's look at today's baseline activity. So I'm going to read out the questions for you and then give you time to answer the questions. And then afterwards, we will do the corrections together. So let's read question 1. What is the source of natural light on Earth? And why is photosynthesis in plants important? Why is photosynthesis in plants important? I'm going to give you 2 minutes to answer these questions. Then after 2 minutes, we will do the corrections together. See you after 2 minutes. Welcome back, grade 8. So now let's answer the questions together. The first question read, what is the source of natural light on Earth? The sun is the source. So if you wrote that one, give yourself a mark. And the second question is, why is photosynthesis in plants important? Why is it important? Remember, we learned about photosynthesis in term 1. If you remember, we learned about photosynthesis in term 1. Do you remember what the role of photosynthesis is or what its significance is? Why is it so important to us? So, the process of photosynthesis is how plants make their food and supply oxygen to other living organisms. So photosynthesis is very important. It is very important. So I'm going to give you 1 minute to write down the corrections. Don't forget to send in your answers to the number that is on the bottom of the screen. Send in your answers. See you after 1 minute. Copy down the corrections. Welcome back. I'm sure you had plenty of time to copy down the corrections. Now let's move on to terminology. These are the important terms that we're going to come across during the course of the lesson. They'll help us to better understand what the different concepts mean. So let's start with the first one, which is our main topic, visible light. What is visible light? Visible light can be defined as electromagnetic radiation that can produce a visual sensation. The next one is wavelength. Wavelength, what is wavelength? Wavelength is the distance between one crest of a wave and the next corresponding crest. And then the next term is frequency. Frequency is the number of waves that pass a certain point every second. And then the next term is spectrum. What is spectrum? Spectrum is a band of colors produced by the separation of the components of light by their different degrees of refraction. And then the next one is refraction. We just spoke of refraction when we were defining spectrum. So now let's define refraction. Refraction is the bending of any wave when it passes from one medium to another of a different optical density. Now let's look at our second slide. We're still on terminology. So radiation, what is radiation? Radiation is the energy that is emitted by electromagnetic waves, and then luminous means emitting light, and illuminated. An illuminated object is one that provides light by reflecting light from another source. And what is to reflect? It is simply to throw back without absorbing. You know how mirrors reflect us when we look at a mirror and how it reflects us. So that is that. Now let's begin our lesson. What is radiation of light? Now, so light can come from different sources. I know in the previous grade, even now in our baseline, we said that light comes from the sun. But we have other objects that can give us light. So light can come from different sources. So objects that give off their light are luminous. Which object can you think of from the top of your head? We have been using this particular object when we're learning about series circuits, parallel circuits, and circuits in general. So objects now that do not give off their light are called illuminated objects. They're called illuminated objects. So the light energy from luminous objects is transferred by radiation. So light is actually a form of energy known as electromagnetic radiation. So we all know that the sun is the primary source. It is the primary source of radiation, this electromagnetic radiation. to the earth. Now, other luminous objects are electric light bulbs and candles. Remember when I said we've been using this object quite often when we're learning about circuits, and these are light bulbs. So light bulbs are luminous. They are luminous. Why do we say they're luminous? Because they give off their light. They give off their light. Another object that is luminous is a candle that has been lit. A candle that has been lit is also luminous. So these are the two examples other than the sun. So let's talk more of radiation of light. So the light energy from the sun, what does it do? It travels through space. Between the earth and the sun, there is space. So the light energy from the sun travels through space, which is a vacuum. Remember, space is a vacuum. There is nothing in there. So it's a space of nothingness. It is a vacuum. So as it does not need particles to be transmitted. So we don't need any particles to transmit the light that we get from the sun. So it travels through the vacuum, that is space, to the earth without any need for any particles. So now, the light travels extremely fast. I'm sure you've heard about the speed of light. Wow, let's quantify it. So light travels extremely fast at approximately 300,000 kilometers per second in a vacuum. That is pretty fast, isn't it? It is very, very fast. So it travels at a very, very fast speed of 300,000 kilometers per second. So can you imagine how fast that is? If you think of a car traveling at 100 kilometers per hour, that's very slow. It's slower. It's way, way slower. So now, where is the sun? The sun is 150 million kilometers from the earth. And it is a luminous object because it radiates its light into space. The sun is very, very far away, but somehow it manages to provide us with this luminous light energy. So it is 150 million kilometers from us. Now, let's talk about the moon. Now that we've spoken about the sun, we see it during the day, it shines on us, it helps us see our way and see different objects. But what about the moon? The moon is not a luminous object, rather it is an illuminated object. So we only see it because it reflects the light of the sun. We only see it because it reflects the light of the sun. So when you're seeing the moon tonight, if there's a full moon tonight or if there's a half moon tonight, just remember that the moon is an illuminated object. We are only able to see it because it reflects the light of the sun. So we can only see things because light shines on them. You can see me now because there's a light shining on me. You can see your friend because there's a light shining on your friend. And it's during the day, so obviously this is the light of the sun. If you're in a room and you have your lights on, you can see the different items and the different objects that are in the room because the light is shining on them. So luminous objects produce light, they produce light, and illuminous objects, you can only see them because now they are reflecting the light. They are reflecting the light. So now let's talk about light energy is radiated from luminous objects. Now, so when light is radiated from a source such as a light bulb or a torch, let's say there's load shedding, there's no electricity, and you're carrying a torch bulb. So a beam of light is actually visible. Let's look at this diagram here. So this person is moving around in the dark carrying a torch bulb. So they are moving in the dark and you can actually see the beam of light such that you can even draw it. You can even draw it and see the direction in which it is going. So you can see a beam of light. So if you are shining a light or if you are radiating a light from a source such as a light bulb or a torch, you can actually see a beam of light. So now how is it possible that you can actually follow that beam of light? This is because light travels in straight lines. light travels in straight lines. If we go back to the diagram, if we look at the diagram where there is the beam of light, so there's a straight line. So light travels in straight lines. So they're not necessarily horizontal or vertical or skewed. Straight line is in straight. So light travels in straight line. Okay, so it doesn't take turns. It travels in a straight line. That's how you are able to see that beam of light from a torch in the dark. So the beam is only visible when particles such as dust or water droplets scatter the light. So you're walking out and most probably there's a lot of dust particles within the air, so you are able to see that beam of light. So that's why when the car headlights show up in the mist, so when there's a mist during the rainy months or the winter months, and then there's a mist, that's why you can see the car headlights showing up well as the car is moving from point A to point B. That's how you are able to see that. That's how you're able to see that. So now, beams of light diverge from their source, forming what is called a cone shape. This phenomenon can easily be seen from the headlights of a car or lighthouse or spotlights or torch beams, if you remember the pictures that I had in the previous slide. So the further the light is, the less the beams diverge. The less the beams diverge. So light from distant objects is taken to be traveling in parallel rays. Do you remember what we said the meaning of parallel is? Lines that never meet. However, from close range or rather close objects, the light is still divergent. The light is still divergent. So now, just to further emphasize on how light travels in straight lines. So this is a stage. It could be a stage or for a concert or a play. Now, so this is a stage and the stage lights are on. So the stage lights are providing light. If you try and follow the light, you can see that the light is beaming down in a straight line. The light is beaming down in a straight line. Of course, my hand is a bit shaky, but you can see that the line is beaming down in a straight line. If you look at this lighthouse, remember the cone shape that we spoke about? Let me try and, there we go. There's our cone shape. So our light source is here from the light at the top of the lighthouse. There we go. So there we go. So when beams of light diverge from their source, when they're diverging from their source, where's the source? That is the source. When they're diverging from the source, they form a cone shape. So there is the cone shape that is formed by this lighthouse. That is formed by the lighthouse. So now let's talk about the pinhole camera. The pinhole camera. So this is basically the pinhole camera. But what else do we know about it? Let's describe it. Let's discuss how it works. Okay, so a pinhole camera, what is it? A pinhole camera is a basic type of camera that shows you how light rays behave, or rather how light travels in a straight line. How light travels in a straight line. So a pinhole camera is used to form an upside down image of a luminous object on a screen. So you see the tree here is upright and the tree on here is upside down. Now let's further describe, or let's further define what this is, this pinhole camera. So a pinhole camera can also be defined as a simple optical device that forms an image without using a lens or a mirror. So we're not using a lens and we're not using a mirror in this case. It's just a simple gadget that is a box and a pin and utilizes light. So let's talk more on the pinhole camera. So how can we make a pinhole camera? So you can make a pinhole camera using an old milk box and a shoe box, and then make sure that they are painted black on the inside. So we've got a milk box there and we've got an old shoe box. So that's how you can make a pinhole camera. So now the viewing hole, the hole where you're going to view through, where you're going to put your eyes through, is made using a pin and at the end, at the other end, the side of the shoebox is removed and fitted with tracing paper. Tracing paper is the paper that you can see through. The very light tracing paper that we use to do tracings when we're doing our drawings. So if it is fitted with a tracing paper, that will form the screen on which the image forms. So light will enter through the tiny hole. Where's the tiny hole coming from? Remember, we made a hole with the pin. We made the hole with the pin. So that is where the light is going to come from. So now it enters the tiny hole and then forms an image on a screen or tissue paper. In this case, we used tracing paper at the back of the camera. So the amount of light that gets into the camera can be controlled by changing the size of the hole of the camera. If you want a very small hole, you can get a very small hole, you can get a bigger hole, but you can change the sizes of the hole. And the sizes of the hole determine the amount of light that comes into the camera. So you can determine that. Now let's look at a picture of the pinhole camera. So we said that the pinhole here that's made using a pin whose size, the size of the hole can be adjusted. The size of the hole can be adjusted. And then so this is the object. This is the object. It's a tree out there in nature. And then we have a image forming. So the image is forming on tracing paper or on tissue paper or any screen that you can find. So that's where the image is going to form. That's where the image is going to form. Now, how does it work? How does the pinhole camera work? So this is how it works. So when light passes through that small hole, the hole that we made with the pin, so when light passes through there, an inverted image of the object being viewed will be formed on the tracing paper. Now, the light rays also cross from the left to the right so that the image is mirrored as well as inverted. Now, what am I saying? Now, let's look at this diagram, or rather, let's use this diagram to explain how the pinhole camera works. Now, the sun shines on the object. What is the object? The object is the tree. So the sun radiates light on the object. So now this luminous object then reflects the light onto the camera. So this is the hole. This is the hole that we made. This is the hole that we made. But however, it appears inverted or upside down. It's going to appear inverted. Let's say the top of the tree is M and the bottom of the tree is N. So when light is radiated onto the tree, the light ray from M is going to go, remember light travels in a straight line. So it's going to go in through the hole and be reflected there. So remember light travels in a straight line. Now the bottom, so which will give us a new, let's call it M prime. Let's call this M prime. And then the light that radiates at the bottom of the tree, which we called point number N, goes through the hole in a straight line and gets reflected there and forms an image there, which we'll call N. We call this point N prime. So that's how we end up with an inverted or an upside down image of the tree on the screen. Now, you can change the quality, or you can adjust the quality of the image that is formed. The smaller the hole gives you a more clear, a more crisp image of the tree, but bigger holes will give you one with a lesser quality or one which is much blurry. So this is just a simple indication on how light travels in a straight line and how we end up with an inverted image on a pinhole camera. So you can actually do this exercise, or you can actually make a pinhole camera when you get home. Just look for a shoebox and an old meat box, a pin to make a hole. Make sure, be careful with sharp objects, and you can get tissue paper or you can get tracing paper and make your own pinhole camera. You can use it to view things during the day, trees, houses, whatever objects you may want to look at through your pinhole camera. Okay, so now let's move on to our first activity, activity 1. Right, so there we go. We're going to load the questions now for activity 1. So now we've loaded the questions. Give the meanings of the following terms. Give the meanings of the following terms. The first one, which is A, is luminous. The second one is radiation. So you need to give the meanings for the following terms. And then question 2, from the pictures below, list the objects you cannot see in the dark and you can see in the dark. So there we go. So we've got objects there. Which ones can you see in the dark and which ones can you not see in the dark? So you need to list them. If you can't list them, just mark them. Send in your answers to 079-578-2908. 2908. Okay, I'm going to give you 4 minutes to answer these questions. Then after 4 minutes, we'll do the corrections together. Welcome back, grade 8. Now let's do the solutions together. Don't forget to send in your responses to the number at the bottom of the screen. Now let's give the meanings for the following terms. We had luminous and we had radiation. What do they mean? Luminous means emitting light or to emit light. If you got that one correct, you can give yourself a mark. The second one is radiation. What is radiation? Radiation is the energy that is emitted by electromagnetic waves. If you're not sure, just go back to the terms that we defined today at the beginning of the lesson and you will definitely find the definitions. You definitely find the definitions. Now let's look at question 2. With question 2, we had pictures. So we said you can mark the pictures or you can list the pictures. It's all up to you. You can mark them or you can list them. Now, which ones? The ones that you cannot see in the dark. So let's say you enter into a dark room. Which of those pictures will you not be able to see? And then which ones will you be able to see if you enter a dark room? So here are the objects. You won't be able to see the table. In the dark. You will not be able to see the pile of books in the dark. And you will not be able to see the clothes. And on the previous slide, I had clothes. You will not be able to see the clothes. So you're most likely to bump into any one of these things. Now, however, question B, you will be able to see a candle in the dark. You also will be able to see a fire in the dark. And you will be able to see a light bulb that is shining. If it's shining, you will be able to see it. So you will be able to see 3 of these items or objects, and you will not be able to see the other 3 of the objects. So you won't be able to see the table, you won't be able to see the books, and you will not be able to see the clothes. You will be able to see the candle light, which is lit. You will be able to see a fire, flames of a fire. You'll be able to see them. And you will be able to see a light bulb that is shining. Okay, so now that we are done with our exercise, don't forget, if you have any questions, if there's something that you do not understand, please do send your questions to the number that is at the bottom of the screen. The number is 079-578-82908. We will send you a response as soon as possible. Now, let's talk about the spectrum of visible light, which is the second half of our subtopic. So we're done with radiation of light. Now we're moving to spectrum of visible light. So the sun radiates what is called white light. So it radiates white light. So what is white light? What makes up white light? White light is a combination of all different colors of light, which you can see separately in the bands of a rainbow. I'm sure you saw the rainbow behind me when we began our lesson today. So now that whole collection of all colors that you find on a rainbow is called the spectrum of visible light. It is called the spectrum of visible light. So that's one interesting thing that we've learned about today. So next time if you see a rainbow, just know that all those colors, the collection of those colors, is called the spectrum of visible light. So now light is called a wave because it travels, and it travels in a regular, repetitive pattern, but you cannot see the pattern that the light creates. You can't see it, but we know that it travels in waves and in a regular, repetitive pattern. What does regular, repetitive pattern mean? It means that it is always the same. The pattern is always the same. It is regular and it is repetitive. It is always the same. So now we said a white light is a combination of different colors of light. So what are the different colors of light that make up the white light that the sun radiates? The first one is red. The second one is orange. Then we have yellow, green, blue, indigo, and violet. So it is red, orange, yellow, green, blue, indigo, and violet. So there is 7 of them. There are 7 of them. Now, so I drew these red, yellow, orange wavy lines just to further emphasize that light travels in waves. It travels in waves. We know it travels in a straight line, but in that straight line, they'll be traveling in waves. So now, each color of the visible light has a characteristic wave. Some colors have long waves, while others have short waves. These are different colors. Some have long waves and some have short waves. So wavelength, I'm sure we defined wavelength when we're doing our terminology slides. So wavelength is the length of one wave pattern. So therefore, the wavelength is the distance between 2 consecutive crests or troughs in a wave, and it is measured between 2 points in a phase. Let's visualize that. What are troughs? What are crests? Now let me show you what they are. So this is how we measure wavelength. So wavelength, we said, is the distance between 2 consecutive crests. So these are crests. Those are what crests are. Those are crests. So the distance between this crest and this crest gives you your wavelength. They have to be consecutive. They have to be consecutive, meaning one must come after the other. One must come after the other. You can't measure from this crest to that crest. No, they have to be consecutive. Now, we said crests or troughs in a way. What are the troughs? The troughs are down here at the bottom. So the distance between here and here, so this trough and that trough gives you the wavelength. It gives you the wavelength. It gives you the wavelength. So these are 2 points that are measured in a phase. Now let's talk more about spectrum of light. So wavelength, we have established that wavelength is measured from one crest of the wave to the next crest, or from one trough to the second trough. And they have to be following each other. One must come after the other. They must be consecutive. So now, note that short wavelengths are measured in nanometers. Remember, we've been learning about SI units. Wavelength also has a unit as well. And the shorter wavelengths are measured in nanometers. In short, you can just represent it as nm. nm. So now, the shorter wavelength, the more waves it will be that will be able to pass through a certain point at a given time, and the greater the energy. So short wavelengths are able to pass a certain time at a certain point at a given time faster, and they have greater energy. Now let's look at the picture with our spectrum of light, of visible light. There we go, there's our spectrum of visible light. We've got our colors: red, orange, yellow, green, blue, indigo, and violet. So we have our spectrum of visible light there. Now we said each color has its own special or its own characteristic wave. Now red is over here. Red is over here, which means red's waves have a longer wavelength. Whereas if we look at violet, from this trough to this trough, you see the wavelength is much shorter and is measured in nanometers, which is 0.0001 nanometers. Whereas with red, it is 100 meters. It is 100 meters. So now we spoke about short wavelengths. And how they're measured in nanometers. As you can see, there are the nanometers there. We also said the shorter the waves, the wavelength, the more waves will be able to pass a certain point at a given time. So over here, we've got our short waves. We've got our short waves. They become shorter and shorter in this direction. So that's why we are saying that energy is increasing from my right to my left. It is increasing from my right to my left. Now, let's talk more on the spectrum of visible light. So now there are 7 colors. We said there is red, orange, yellow, green, blue, indigo, and violet. So there are 7 colors in the visible light spectrum, and each of these colors have a different frequency and wavelength. As you saw in our previous slide, we had that diagram with the different wavelengths. So these colors can be easily remembered if you claim this acronym, which is Roy G. Biff. Roy G. Biff. Now, Roy G. Biff, R for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, and V for violet. So, out of these 7 colors, we have 3 colors which are red, green, and blue. These are called the primary colors of light, and these are quite different from the primary colors of paint. Now, if the 3 primary colors of light are mixed, they form a white light. So we said the 3 primary colors are red, green, and blue. If we mix red and blue, we get a different color. If we mix green and blue, we get a different color. If we mix green and red, we get a different color. But if we mix all these 3, this is the point where I want us to focus. There, we get white light. We get white light. So now let's learn about dispersion of white light. We said white light is a combination of Roy G. Biff, red, orange, yellow, green, blue, indigo, and violet. But now let's talk about dispersion of light. So the speed of light changes slightly depending on the medium through which it travels. Is it traveling through my glasses? Is it traveling through the window? Is it traveling through a vacuum? So the speed of light is altered by the medium through which it is traveling. So it is faster when it's traveling through space. That's why even if the sun is 150 million kilometers away from us, it still shines on us and it still gets hot. Now, so when it is traveling through space, it moves very fast at 300,000 kilometers, right? Now, but slower when it's traveling through an optically denser medium, such as a glass or water, such as a glass of water or all water. Now, so when white light strikes the side of a glass prism, it goes from an optically less dense medium, which is the air, to an optically more dense medium. So a prism block or perspex that can split white light into different colors of the visible spectrum. So that's how we can see the different lights of the visible spectrum if we have a prism. So now this causes the light rays to slow down. And what else happens? They bend. And this phenomenon is called refraction. Now let's look at the glass prism. I have a picture of a glass prism with me. So we've got our white light entering here. Just going to write white light. What our white light? So once it gets to the block of perspex or the block of glass, once it strikes the side of the glass prism, it is now moving from a space where it was less dense to a space where now the medium is more dense. So now it's going to bend the light. You see, it's moving in. We said light moves in a straight line. So we expect it to move in that direction in a straight line. But when it hits the side of the prism, it bends. You see it bend there. And then what else happens? It slows down. It slows down. And what else happens? It splits into the combination of colors that make up white light, which are the 7 colors. You can see them here, which are the 7 colors that make up white light. Okay, so more on dispersion of light. So the sides of the triangular prism are angled. Remember, triangles are angled. Now the sides of the triangular prism are angled, our triangles are angled. So the light rays strike the object at an angle. So they strike the object at an angle, it bends the light, and then disperses the light. So the color of light we see depends on the wavelength and frequency. But what is frequency? Frequency is the number of waves that pass a point each second. That is frequency. So there is our light, there's our triangular prism, there's our white light coming from this direction. It strikes the side of the object, bends the light, and then it splits or disperses it into the different colors that make up white light, which is red, orange, yellow, green, blue, indigo, and violet. And remember we spoke about frequency. So frequency is the number of waves that pass a point each second, that pass a point. So now let's look at this diagram here, this diagram of visible light. We said that each color has a different wavelength. Just to show you, so this one has been measured, which is red, has been measured from this trough to that trough, and we have a distance of 700 nanometers. So our range is 700 nanometers and 400 nanometers. Now, the one with the smallest, which is violet, we can measure from this trough to that trough, will give us a wavelength of 400 nanometers. Now, so red and orange, which we find here in the beginning, red and orange light has the longest wavelength and the lowest frequency. So it doesn't move as fast. It doesn't pass a point or move to a point as fast as the ones with the least. So the ones with the least is 400 nanometers, which is your indigo and your color violet. So violet and indigo and the blue light have the shortest wavelength and the highest frequency, and because of the highest amount of energy. Remember we said as we are moving from this direction to there, our energy is increasing. Our energy is increasing. Now, so the different light waves are all refracted at different angles, which spreads them out. And this phenomenon is called dispersion. This phenomenon is dispersion. It's not always easy to distinguish all the colors from the light spectrum. Think of a rainbow. You've seen a rainbow before. Did you ever imagine, or can you remember seeing 7 different colors? So sometimes it's not easy to distinguish between all the colors in the spectrum. So the diagram below will show a clear distinction between one color and the next, but in actual reality, the colors blend into each other and you can't see them. So I've got a diagram on the right hand side. The diagram shows us a clear distinction between one color and the next. And then on my left, here we have what we see in reality. Well, this is my take, this is my observation. If you see anything different, if you're able to distinguish between the colors in the rainbow, please do tell me. Do send in your responses to 079-578-2908 if you're able to distinguish. So let's see if I can distinguish between each of the 7 colors. So I can see red on the rainbow. I can see a bit of yellow, I can see green, I can see blue, and I can see violet. So red, yellow, green, blue, and violet. So of the 7, I was able to see 5. If you can see all of them, please let me know. Just send it through the WhatsApp number. Now, so how does a rainbow form? A rainbow forms after a storm because there are tiny drops of water in the atmosphere. and they act like a glass prism. Remember, less dense environment to a more dense environment. So the water droplets are able to disperse the light from the sun and reflect it towards the direction of the light. So this makes it possible for us to be able to see the rainbow, but only if the sun is behind you. So there is my rainbow over there. There's been a storm and there's still some water droplets in the air. The sun shines on them or radiates light on them, and then we will be able to see the spectrum of visible light due to the dispersion of the white light, So now, which brings us to our second activity of the day. So, first question, when are you able to see a rainbow? What is meant by the dispersion of light? And white light consists of a range of different frequencies and wavelengths. Well, A, give an example from nature that shows you how white light can be separated into different frequencies and wavelengths. And then B, name the different colors that make up the spectrum of visible light. I'm going to give you 4 minutes to answer these questions. Then after 4 minutes, we'll do the corrections together. We have a learner from Soshanguwe Tech SOS sending in answers. Well done. Well done for getting all your answers correct, or your questions correct, rather. Now, let's answer the questions. When are you able to see a rainbow? When are you able to see a rainbow? You can see a rainbow. How? So this is how a rainbow forms. So a rainbow forms after a storm because the tiny drops of water are still in the atmosphere and they act like a glass prism. So when rainbow drops, when water drops, disperse light from the sun and reflect it towards the direction of the light, and this makes it possible for us to see the rainbow only if the sun is behind you. Now, what is meant by dispersion of light? What is it? It's actually a change in direction of the light when the colors are spread, when they spread out. So that is the dispersion of light. And then our third question is, what's response number 1? Give an example in nature that shows how white light can be separated into different frequencies and wavelengths. It's when a rainbow forms. So that is our nature example. And name the different colors that make up the spectrum of visible light: red, orange, yellow, green, blue, indigo, and violet. Don't forget the acronym. Don't forget the acronym. Roy G. Biv. Roy G. Biv. Okay, so now let's wrap up our lesson. What did we learn today? Today we learned that light is emitted by a luminous object. Light travels in straight lines. Light travels very fast through an empty space, like the space between the earth and the sun. What else? White light is made up of a range of waves with different frequencies and wavelengths. And the 7 colors that make up white light are red, orange, yellow, green, blue, indigo, and violet. And violet has the shortest wavelength and the highest frequency, while red has the longest wavelength and the lowest frequency. And then a rainbow forms. How does it form? It forms when light falls on water droplets that are in the air after a storm. Okay, so there is our homework activity. I'm going to give you 1 minute to quickly copy down the questions, and then we will end our lesson. All right, grade 8 learners, in our next lesson, we're going to be explaining opaque and transparent substances. Opaque and transparent substances. Thank you so much for joining me in this lesson. Until next time, see you. Don't forget to do the homework. Bye-bye.